Good morning. We have midterm 3 coming up, and so let's take a look at some review problems. As the same as before, what I have is I have a couple of midterms from previous years that we can go back and take a look at the problems, see what these midterms were like. You know, there's always this question of, were the earlier years midterms easier? Were they harder? I've tried to pick out ones that have what I feel like are some fairly challenging, pretty good level of difficulty. Anyway, let's go ahead and take a look at some of these. So problem number 1 that we have is from it's a chapter 12 type problem. It's static equilibrium, and it has to do with a ladder set up against a wall. Now, the idea here is the wall itself is frictionless, and that saves us from having to deal with a frictional force along the wall. Now, the floor definitely needs some friction. So when we do the force diagram, which is what part A asks about, let's go in and do the force diagram for this. I'm going to have, for the ladder, there's going to be a gravitational force, and I can place that gravitational force at the center of mass. So I'll place that right along, well, I place it halfway along the length of the ladder. Now the ladder is 14 kilograms, it's got a length of 2.5 meters, it's angled at 30 degrees, there is a static coefficient of friction on the floor, 0.40. So I've got the gravitational force. Now I've got 2 contact forces. I have a contact force with the wall, and I have a contact force with the floor. And both of those contact forces can be placed perpendicular to the surface. So the force from the wall coming perpendicularly directly away from the wall, and the one on the floor directly vertical, perpendicular to the floor or the ground. So I'm calling those N1 and N2, and then in addition I need a frictional force at the floor. So those 4 forces, I'm going to need to be able to keep the ladder in equilibrium using those. Now if I just look at vertical directions, I can see that N1 needs to be large enough to match mg. So N1's magnitude is equal to the magnitude of mg, N1 equals mg. Similarly, in the horizontal direction, I can take a look at the forces in the horizontal, and in the horizontal direction, N2 coming away from the wall and the frictional force, those two have to be the same. Now, what we should be, recognizing now that you guys have some experience with these types of problems is that N1 equals mg, but they're not lined up. They're displaced away from each other, and that says that there's going to be some kind of a torque. N1 and mg together, the forces cancel out, but because they're displaced, N1 and mg together are tending to rotate the ladder this way, what we might call the negative direction. On the other hand, the frictional force and N2, those 2 forces cancel out, but their torques do not. So the 2 torques combined are going to tend to rotate the ladder the other way, and we just have to make sure that the torques cancel out. Now in the problem it says draw the diagram. I think we got all the diagram drawn. B says calculate the magnitude for each of the forces. Now some of these I can just jump right in and calculate. So it turns out that mg, that's one of the 4 forces, m times g is 137 newtons. Done, right? I got full credit on that, I hope. N1 is going to be the same as mg in terms of magnitude. So that's also 137 newtons. Done. There's 2 of the forces. Now, I can't get N2 and I can't get F of S. Now, I do have a coefficient of friction, but this is static friction, and I'm guessing that this frictional force, it's not at the limit, it's not at its maximum value. If I set a ladder up, it's probably within, the frictional force being used is probably within the maximum value. So I can't get the frictional force either. So what I'm going to have to do is use torques. Now, I'm thinking point A, where the ladder makes contact with the floor, that's probably a good place to measure torques, because if I measure torques here, then N1 will drop out of the equation and the static friction will drop out. If I measure torques from here, then mg and N2 will be in my equation. That sounds promising. So I did that. Now, there's another diagram here. There's a diagram here showing the rectangular shape of what's going on here. The ladder is diagonally placed through that rectangle, and here's point A at the corner of the rectangle. N2 has a lever distance from here to here. So that is the lever distance, and that is L cosine of theta. So N2 with a lever distance of L cosine theta is equal to, now this is mg, and mg has a lever distance of 1/2 this bottom of the rectangle. So that would be 1/2 L sine theta. So make sure you're understanding all these lever distances. These are often the most difficult part of some of these problems, is making sure that you're clear on the lever distances. And if any questions at all, stop by office hours and let's get that looked at. All right, so this is measuring torques around point A, and from that I can solve for N2. Now the L's actually drop out, which says, you know, all the stuff that we're calculating here, it doesn't depend on the length of the ladder. It could be a ladder with twice the length, as long as the mass is still 14 kilograms and the angle is the same, I'm going to get the same set of numbers. So kind of interesting to think about that. If I solve this for N2, I get 1/2 mg. The L's cancel, but the sine over the cosine gives me a tangent. I can plug in the angle, and I got 39.6 newtons. Now, once I get N2, the static frictional force is the same thing. So 39.6, 39.6, done. I've got all four forces evaluated. I know how much force each one is, and I got a force diagram that shows where each force is being applied. All right, that all sounds good. Now in part C it says, what if I change the angle? What's the largest angle that we could set the ladder at and still have it not slip? Well, part C, now that's asking about maximum static frictional force. So what's going to happen is, if I place this ladder vertically, I won't need much friction. As the angle increases, I am going to need more and more friction in order to hold the ladder in place. So again, let's come back to the diagram here. The maximum static friction force I could get would be mu sub s times N1, which would be mu sub s times mg. So now the maximum static frictional force that I calculate from that is 54.9 newtons. So that would be larger than what we calculated in part B. So it says the frictional force could be as large as that. If that's the case, then the angle has increased. And what we can do is come back to this formula. We can come back to this formula right here and go back and solve that over again, this time putting in the maximum value for N2 and calculating the angle from that. So putting that back into the tan theta formula, I ended up with tan theta equals 0.80. The angle I got was 38.7. So it says, yeah, the angle of placement for the ladder could be increased, and it could be increased all the way to 38.7 degrees, and the ladder would, right at that point, it's right at the point where it's about ready to slip if I go to 38.7. So, good problem. I think we looked at that example. We may have asked the same questions, maybe a little differently. Anyway, this is a good example for static equilibrium. Let's take a look at this next example. So here, what I've got is, I have a piece of wood floating in the water. Now, the volume of that wood is 50 cubic centimeters. 27% of its volume is out of the water. You know what that means? 73% is in the water. So here's my, did they ask the diagram? Yeah, no, they didn't. I drew a diagram. Here is the wood floating in the water, and the wood has a mass, mg, drawing down on it. Now the mass could be written as density of the wood, density of the object, times the volume of the object, that's the entire volume, times g. Now the buoyant force depends on the density of the fluid and how much of the fluid is being displaced. So the volume of the object, of the piece of wood, is the full 50 cubic centimeters, but the volume of the fluid being displaced, that's at 73% of the total volume. So 36.5 cubic centimeters of the wood block is below the water, and the 13.5 cubic centimeters is above. Now what I can see with these two formulas is those two forces have to match. So if I set B equal to mg, the g, the gravitational field, drops out. And again, when the gravitational field drops out, that tells us this works on any planet. We'd get the same answer if we were doing this on Mars or on Jupiter or something like that. So that says the density of the wood times the wood's volume has to equal the density of the water times the displaced volume. And so the density of the wood, which is what they're asking in part A, is the density of the water times this ratio of volumes. And that ratio of volumes, well, I can just go back to the 0.73 ratio. So it says that the wood has a density of 0.73. The wood is only 73% as dense as the water, and that means that the wood, 73% of it displaces water, and that's enough to support the wood. That creates a large enough buoyant force, which is coming from the fluid pressure differences. That creates enough of a buoyant force to hold the object above the water. Now in part B, what we're going to do is take that same piece of wood and put it in a mystery fluid, a mystery liquid of some sort. What's the density in the other liquid? Okay, this time the wood has 35% sticking out of the fluid, out of that liquid. I think this liquid is denser, right? It's providing the same buoyant force, but it's requiring less fluid displacement. So let's see what this works out to be. Now, we already did the force diagram, and what we said was in that first part, the density of the wood times the volume of the wood equals the density of the water times the volume of water. Well, that could be any fluid, and that's originally how I drew the diagram in terms of any fluid at all. So this time, well, there's multiple ways we could solve this. I'm gonna take these last two statements. The density of the fluid times the volume displaced equals the density of the water times the volume displaced, and solve for the density of the fluid. Now, when it was in the water, 0.73 of the total volume was water displaced. When it's put in the unknown fluid, or the known fluid, whatever, that's going to be 0.65. So that looking at those ratios, the V naughts drop out. I'm using the density of water, 1 gram per cubic centimeter, and it's 1.00. This new liquid that we put the wood in is at 1.12. Aha! Maybe it is, I don't know. Anyway, it's denser than water. So 1.12 grams per cubic centimeter. Now in part C, you're going, okay, fine. We got the densities of the wood, we got the density of the liquid. What if we now go back to the water where, what was it, 27% of the volume was sticking out? What if we start putting little rocks on top until the block is just level with the water? Now, this is a little bit open to interpretation, so if questions come up on an exam, midterm, let me know right away. You know, I'll have office hours going on. You can just check into office hours, you know, just come right in and ask whatever questions you've got. So, or during an exam in general, you can just ask questions as needed. So the idea of writing the question, when I did write this one, is that we're going to load this until the block is right at the surface. Now, I guess it's true, we could continue loading it until the rocks too were below the water, but that wasn't the intention. So this is the intention of what things are going to look like. Now, what we can do then is we can go, okay, if the block slips farther so that it's completely within the water, the entire volume now of the block is displacing water, that's a larger buoyant force. And the buoyant force now is going to be the density of the water, but it's going to be times the volume, the full volume of water that's been displaced. And so now what I did is I took the density of the water times the volume being displaced. That corresponds to 50 grams of water that have been pushed out of the way. And so what we can say is that buoyant force, the rho Vg, is now equal to the mass of the block times g plus the mass of additional rocks placed on top. Now the g's cancel out. You know, we keep seeing in these buoyant force problems that the gravitational field factor drops out, and as a result we can do the problem in terms of just directly the masses that are involved. And so the mass of water being displaced is 50 grams. Now the mass of the wood, taking its density times the volume, is at 36.5 grams. We saw that earlier. So 15 grams minus this, it says that we could add in 13.5 grams of rock, little tiny pebbles, little tiny pebbles. This is a tiny block. I could put 13.5 grams on, and that would bring the block so that it's level with the surface of the water. That's the idea. Now we're not including surface tension, we're just thinking of this in terms of purely a buoyant force problem. Alright, so I like this problem. I like them both. I like all these. So again, I think this is a good representative set of the types of problems that you might run into. Our midterm will have the same format, 4 questions with parts A, B, C, D. Let's take a look at one more of these. So in problem 3, we have a frictionless lower surface, and there is a block attached to a spring with a K value, and it's oscillating back and forth. Now we take another block and set on top of it, and then we try and let these oscillate together. Now, to have these oscillate together, I do need friction between the two blocks. So the lower surface, frictionless, the friction, the two blocks surface, there's friction between those. Now, the spring is making sure that the lower block oscillates back and forth. What is it that's making the upper block oscillate back and forth, and that would be the frictional force. So I'm depending on friction to keep the upper block from sliding back and forth as this thing oscillates. Now, at low amplitude, the accelerations won't be that large, and I won't need that much force. But as the amplitude gets larger, as I let this thing oscillate back and forth at larger and larger amplitude, everything speeds up and all the accelerations are going to go up. And so that says that at some point there won't be enough friction to keep the upper block from sliding. So let's see what the numbers look like here. The upper block is 2 kilograms, the lower block is 5 kilograms. The spring stiffness, 240 newtons per meter, and again, the lower surface is frictionless. The coefficient of static friction between the two blocks is 0.50. Now it says, first of all, draw some diagrams showing all the forces acting on the blocks. Now, for the upper block, that would be M1G, and I guess I'm using little m. So little m and big M, that's going to be mg, normal force 2, is that what I called it? I guess that's okay. So mg, normal force 2. There's going to be a static frictional force that's proportional. I hope I got this right. Yeah. So the static frictional force at its maximum is going to be mu sub s times n2, and n2 is going to be the same thing as little mg. So that's the upper block. Now the lower block has a mass of 5 kilograms, and it's big M, and that's the gravitational force. Now there's a contact with the table, N1, and there's a contact from the block above. So the lower block is being pushed down with force N2 because of contact with the upper block, and it's being pushed up by the table. So it's being pushed in 2 directions by 2 different normal forces. And then the force of the spring, I'm going to write as Kx, and that's only acting on the lower block. Now, the static frictional forces are going to be equal in magnitude, opposite in directions, along the surface between the 2 blocks. So when the spring is pushing on the lower block with Kx, that's creating an acceleration in that direction. The upper block is experiencing a frictional force in the same direction as Kx. The lower block is experiencing a frictional force opposing that. Now if I take the top block off, the lower block by itself is going to oscillate back and forth faster. Putting that top block on creates an opposing frictional force for the lower block, and it results in more mass for the system. So, so I think we've got all the forces looked at, and the orientations match up, and that would be expected that you could. Now, the accelerations, this is an oscillatory problem, right? This is coming from chapter 14. This is like fluids, chapter 13, chapter 14 here. The Kx is going to be reversing directions. So what's going to happen is this force of Kx is going to be in this direction half the time, but the other half the time it's going to be this way. Now when Kx reverses, so do these frictional forces. So you need something in the diagram, or write a quick note explaining why the forces have the orientations that they do. All right, and then the force diagram is fine. And then, there's only part B. How much could that require us to do? What's the maximum amplitude possible such that the blocks don't slide? So stay together is not the best description here. I'm going to change that right now to say what is the maximum amplitude of oscillation such that the 2 blocks do not slide at all. The static friction is enough to keep the upper block moving right along with the lower block. So what I did was I went back and I thought, you know, it wouldn't be bad to just write down the kinematic formulas for oscillation. You know, oscillations are very different from constant acceleration, and so it's a good reminder as to how this works. Now, if I take a look at the acceleration, what I can see is the largest acceleration that the upper block needs to undergo is at the extreme displacements, and it's given by omega squared times a. So the largest accelerations is when the block is slowing down, stopping, and then reversing direction. That's the points where the acceleration is the largest, and that's given by omega squared times amplitude. Now, omega squared for an oscillating object is given by the spring constant divided by the mass of the system. As long as that upper block is being moved back and forth with the lower block, that effect of additional mass will show up in the frequencies of oscillation. So I want to use K over combined mass here, and I can treat the two blocks as being one. So kinematically, this is what we are expecting for the maximum acceleration. Now, that's related to amplitude right here. So this is the omega squared. That's going to get plugged back in. That's the amplitude that we're interested in. So let's take the omega squared and put that out front. So this is now a statement of the maximum acceleration. Now, the other way we can look at the acceleration is to go back to the force diagrams and say that the maximum acceleration for the block on top is given by the maximum frictional force divided by m. So it's the frictional force, the static frictional force, and I need to have the amplitude at a point where we never exceed, during the oscillation, we don't exceed that value. And so the maximum static frictional force would be mu sub s times n2, which is mu sub s times mg. That says the maximum acceleration would be given by, the maximum acceleration that the friction can handle is given by mu sub s times g. I know what the mu sub s is. That gives me information about the static friction available, and the largest acceleration that the friction can handle is mu sub s times g. So I can put those two things together. I can say this is telling me the largest acceleration possible given the limitations of static friction, and this is a kinematic statement explaining, you know, how I can determine the maximum acceleration. Those two get set equal to each other, so I can bring the mu sub s g down and set that equal to my kinematic statement and then solve for a. So here is the maximum amplitude. It's mu sub s times g times the two masses divided by the spring constant. Now everything here needs to be in standard units. The coefficients of friction are unitless, and what it worked out to be was an amplitude of 0.143 meters or 14.3 centimeters. All right. So that seems reasonable. So anyway, that's the idea. So it involves an understanding of how the kinematics works during oscillation, and then it also involves understanding how frictional forces work, and how they would be able to hold an object in place as it oscillates back and forth. Okay, let's get this last problem, and then we'll take a break. The last problem here coming from, now is this chapter 15 or 16? Yes, it is, because 15 and 16 both look at standing waves set up on strings. So this is representing those last couple chapters. So 12, right? 13, 14, 15, 16. Here is a picture of a string in first harmonic. Now here's harmonics 1, 2, 3, 4. That's first harmonic. The length of the string is 30 centimeters. The linear mass density is 7 grams per meter. The tension is at 35 newtons. They ask what the wave speed is. That's the tension divided by the linear mass density square root. Putting that in, I've got a wave speed of 70.7 meters per second. Now remember, even though it's a standing wave, we can still talk about wave speed. That's still a meaningful quantity to go in and calculate. And so that's how fast disturbances propagate along that string. Now in part B, they're asking about wavelengths and frequencies. I couldn't help myself. I just had to draw the 4 harmonics. I'm surprised I didn't ask for that. That definitely sounds like something I would ask on a midterm. If I'm asking about standing waves, is go ahead and draw those 4 harmonics. Now the formula we derived for the wavelengths is 2L over N, and in this problem the N is 1, 2, 3, or 4. So I went in and calculated the wavelengths for the 4 harmonics. Now the frequencies, I can get them by taking the speed of the wave and dividing by the wavelengths. So for the first harmonic, I used the wave speed divided by wavelength number 1, and I got 118 hertz. Now that's audible. That's something that we can hear, and they ask about that in part C. Now, I could go through and do the speed of the wave over wavelength 2, speed of the wave over wavelength, but what we found, what we derived in class earlier, was that the nth harmonic is n times the first harmonic. So that seems easier. I'm just going to go ahead and take that 118 value, multiply it by 2, multiply it by 3, multiply it by 4. Now you're seeing a little bit of round-off effect here. I kept this original number in my calculator and then multiplied it by 2, 3. By the time I multiplied it by 4, I was seeing, instead of 472, I got 471. Point something, something, something. Anyway, that's kind of the way the formula is going to work. So those are the 4, and they're all audible. Those are all within the range. Human hearing runs from, we say 20 hertz to 20,000. Those are easily all within the range. Now, in part D, we change one thing. We change the tension. So we come in, maybe, is it a guitar string? Whatever. We go in and we reduce the tension? Yeah. So we lower the tension. So let's reduce the tension in that string. That lowers the wave speed, and that does not affect the wavelengths. The length of the string has not changed. We didn't change it. We could have, but not in this problem. So the length of the string did not change. The wavelengths are all the same. So I can just refer back to part B. Now the frequencies will be different because the wave speed has lowered. All the frequencies are going to come down, and you can see by how much, proportionally to how much the wave speed has come down. So the new wave speed is at 65.5, and the frequencies then have reduced to multiples of 109. And that's it. All the frequencies are there. So again, this is a good collection of problems. It's not complete, so this is not everything involved in reviewing for the upcoming midterm, but these are certainly 8 problems that are going to be useful as part of your review, and maybe these are good problems to go ahead and start with, and then go back and start reviewing through homework and lecture examples, as much as time permits. So as always, if you've got questions, stop by. I am going to go ahead and take a break right now. Let's take a break. We'll come back, and we do have one more set. So there's 8 problems here. This is the first 4. After break, we'll take a look at the next.